Before moving on to other topics in deformable mechanics, I would like to say a few words about design. So we have this very simple problem that we've been looking at, which are bars that are subjected only to axial loads. And I just wanted to say a little bit about design of such systems. And in particular, I'd like to say a little bit about stress-based design and factors of safety or safety factors. So if you have a common metal, its stress strain behavior starts off linear elastic with the Young's modulus of E, but at some value of stress you reach a yield point where you have plastic flow in the material and the response becomes nonlinear. There's usually an ultimate stress, so peak stress, and then it kind of falls off and eventually the material fails. And we have ways now of calculating internal forces, strains, and in particular stresses inside systems. And I just wanted to say a little bit about the use of stress as a way of designing, say, the proportions of such systems. Typically, when you design things, there's an allowable stress for the object that you're designing. And so we'll have an allowable stress, we'll just call it sigma A, and that's typically it's usually the yield stress or it's the ultimate stress. So sometimes you allow the system to deform past the linear elastic range into the plastic range, but often you limit the deformations to the elastic range. So if it's limited to the elastic range, you'd have sigma A equals sigma Y, or if you're allowing it to the plastic range, you may allow the sigma A to go all the way up to sigma U. Now, in any real system, there are a lot of uncertainties. So for instance, the load is often rather uncertain. Like if you're designing a bridge, trucks go by, cars go over it. You don't really know what the maximum load on the system is. There's a lot of uncertainty there. Likewise, when you manufacture an engineering system, there's also a lot of uncertainties in the manufacturing process. The geometry is often a little bit uncertain. I mean, there are tolerances, but there's still uncertainties. Even the properties are uncertain. You may call out for specific type of steel or aluminum, but you may not quite get that in reality, and so there's some uncertainties there too. Likewise, the analysis is also in a way uncertain because we've created a mathematical model of the physics, but that's only a mathematical model of the physics, so it doesn't produce an exact result for the response of the system. So you always have to keep that in mind. And because of these uncertainties, you want to have some margin of safety or factor of safety between what you design for and what you allow. Okay, and so in that case, what we do, a very simple way of doing design, this is not the only way of doing design, you say that there's a factor of safety, and that means that the ratio of the allowable stress to the design stress. So the design stress is what you calculate. So you will set a factor of safety. Suppose you set a factor of safety of 3. That means you're going to keep the design stress 3 times less than the allowable stress. So that gives you a big margin of safety there. And in different industries and in different applications, you have different required factors of safety. And of course, that's a very simple way of doing design, but it's often the way design starts. And then you can use more complex probabilistic design methods later on. But so for instance, in mechanical engineering with rotating machinery, for instance, the factor of safety may be 3 on yield or 4 on the ultimate stress. In civil engineering applications, it's often something like 1.6 to 2 on the yield stress. And in the aerospace industry, they're even lower, something like 1.2 to 1.5 on yield. And the reason for those low values in the aerospace industry is if you use larger values, then things like planes will be too heavy because the proportions of the members will be rather large. So they work very hard to get their analysis done right. They work very hard to get their manufacturing and their properties done well so that they can work with smaller safety factors.